Okay, I'll be honest. The idea of covering thermal interface materials felt like reaching deep into the reviewer bag of tricks to pull out the dusty old lint roller. But then I realized that this unassuming tool actually tackles the biggest bottleneck plaguing our silicon dreams. But what does that mean exactly? Well, as chip makers keep squeezing more power into smaller spaces with epic clock speeds, core counts, and data center accelerators where space and weight are infinite. But that's changing. Microfluidic wizards have shrunk these loops down to fit inside a 7mm phone case. Well, the answer lies in the unique properties of the working fluids. By carefully selecting a fluid that boils and freezes at temperatures well beyond normal operating ranges, these loops stay safely sealed even when dunked underwater. The real trick is handling pressure. My favorite innovation comes from Fantex, a company spun out of MIT and backed by DARPA. Their breakthrough: a two-phase liquid cold plate with an ingeniously simple pump that uses the phone's existing vibration motor to passively suck up coolant, cycle it through the heatsink, and dispense it around the chip. The logic is impeccable. As SOCs consume more power and generate more heat, thermals limit performance, battery life, and user experience. If you enjoyed this episode, smash that like button, subscribe for more tech tailies, and turn on notifications for more challenges, experiments, and real talk from the front lines of tech. And if you want to help us answer big questions about the future of humanity, consider becoming a patron at our website. There's exclusive perks like blooper reels, patron casts, and early access. Until next time, stay frosty. Liquid cooling solves this by efficiently wicking energy away from the silicon, allowing chips to run faster, cooler, and more sustainably. Manufacturers are hard at work shrinking microfluidic loops to phone size, mastering challenging fabrication techniques, and finding ingenious ways to miniaturize key components. Apple leads the race, but fierce competitors hot on their tail, promising products in the next 1 to 2 years. Once the dam breaks, we'll see dozens of designs hit the market. The true challenge is mastering manufacturing at scale to drive down costs. But the payoff is enormous. We can expect double-digit performance gains, massive battery savings, and cooler operation even in blazing heat. Liquid cooling won't just be it will be essential for every powerful mobile device. This is the beginning of a frigid future. Phones will run faster, last longer, and stay cool under fire. The age of the liquid loop is upon us. This could bring the same radical thermal improvements without requiring any extra space or adding moving parts. The only downside is that the pump works best on the benchtop, and it remains to be seen whether it can handle the rigors of daily carry. Most electronics are manufactured to operate at near atmospheric pressure. For example, Apple's own image signal pipeline processes over 1 billion pixels per second, taking 10 seconds to crunch a 48-megapixel Pro RAW burst. With liquid cooling, the ISP stays at full tilt, so the burst crunches in half the time. Liquid loops also unlock more efficient computational photography for AI-assisted depth maps, light fields, and more. With sustained performance, Apple's LiDAR scanner can map a room-sized backdrop for Vision Pro's mesh. Plus, you can tether for hours to stream gameplay or watch movies without cooking your poor iPhone. Performance unleashed. So a sudden change in external pressure can wreak havoc on these miniature systems. But the team has you covered. They meticulously machine each component to tolerate extreme pressures and carefully select materials that minimize expansion and contraction. The result is a rugged system, impervious to most of the horrors you can inflict, including accidental drops and the crushing pressures of commercial airplanes. Now, I've taken this thing on 4 flights around the world, over 50,000 miles, and not a single leak or issue. They achieved this feat by weaving together 3 key components: an ultrafine vapor chamber, a graphite heat spreader, and capillary wick microchannels thinner than a human hair. When Apple files a patent, it often prefigures upcoming changes to their product line, and the latest batch reveals tantalizing clues about the rumored iStrace workload balancer inside the iPad Pro. Looking deeper into the gory details, we find references to using on-die thermal diodes to sense temperatures across different parts of the A series. By analyzing this data, iStrace can dynamically shunt work across multiple cores, in perfect lockstep with the capillary wicks that deliver fresh coolant around the A series. That means faster sustained performance, reduced thermals, and cooler batteries. Some patent filings even hint at inkjet printing these microfluidic networks directly onto wafers, dramatically lowering manufacturing costs, while others suggest embedding a pressure sensor to monitor coolant levels, or even a tiny resistive heater to preemptively evaporate some coolant for environments below freezing. By understanding the physics and chemistry at play, Apple could optimize the next generation of silicon to thrive with liquid cooling. Together, they form a closed circuit that circulates a small amount of coolant, usually a special non-conductive liquid around the A19 die. When the processor heats up, it sends a spike of energy into the baseplate, which warms the vapor chamber. The coolant inside rapidly evaporates, turning into vapor and sucking up even more energy. As the vapor rises, it flows into the hollow mid-frame, radiating its heat into the surrounding aluminum shell. In the process, it condenses back into liquid and wicks back down to start the cycle again, all without pumps, fans, or any moving parts. All hail the mighty thermosiphon and cutting-edge renders, all within the same tiny 7mm enclosure. The inevitable byproduct is heat that could look like channels or dimples that exploit the internal pressure differentials to drive coolant flow like miniature geysers. The advantage of embedding the cooling loop directly into the phone is that the coolant can maintain intimate contact with the A19 die, potentially dropping temperatures by another 10 degrees versus today's interface materials. However, integrating the loop poses some unique manufacturing challenges that Apple may or may not be willing to tackle anytime soon. For now, the best way to get a glimpse of this tech is by picking up a prototype loop from Hong Kong upstarts like Frozone Korea. Their approach involves replacing your rear glass with a sandwich of copper and graphene, 0.3 of a millimeter thicker but tough enough to laugh off drops, thanks to Gorilla Glass Victus 3, fused over a sintered copper lattice. The added thickness allows room for a miniaturized liquid cooling loop containing a supercritical fluid like carbon dioxide or a fluorinated liquid like 3M Novec. These coolants have extremely high thermal conductivity, but remain liquid over a wide temperature range, enabling aggressive clock speeds while fending off battery damage and ghost touches. Thanks to its intimate contact with the A19 die, the Frozone loop delivers impressive improvements in sustained performance, dropping CPU temps by 10 degrees Celsius, increasing average frame rates in games by 5% and reducing battery temp during long photo shoots by a whopping 35 degrees. What's more, the added mass of the copper backing helps dissipate vibrations and reduce rattles at highway speeds. It's a win-win. That heat doesn't just disappear. It attacks battery life, throttles performance, and scorches poor, unsuspecting fingers trying to snap that perfect picture. So why does the surface remain so cool to the touch? You might assume the phone's dinky fan is spinning up, but nope, there is no fan. The secret is thermal interface material, or TIM, a composite of aluminum, copper, and specialized graphite films, sandwiched around the A-series die that draws waste heat away from the brains, dissipating it through the body. But this heat spreader has limits. As cameras and apps push the A19 to its edge, the TIM can only do so much before it hits thermal saturation, at which point the whole phone starts to cook like an undercooked lobster. But did you notice that in the intro? Despite the rising thermals, the phone never dims the screen, throttles the camera, or cuts the audio. How? By shedding its coats like an Arctic fox, shedding its thermal layers one by one until every ounce of energy goes to keeping the party going. That's the promise of liquid cooling. If I could film the insane stunts on my iPhone 15 Pro, sure I'd need a helmet cam rig, a few thousand feet of tether, and a sidearm rig to stabilize the footage while battling whiteout conditions on a 13,000-foot glacier. But none of that would matter if not for the quiet miracle occurring beneath the glass. Welcome to the frosty frontier, where smartphone thermals meet a revolution poised to turn pocket furnaces into chill performance beasts. Let's dive into it. First things first. I don't think anyone really bats an eye when you say that iPhones cook. But here's the kicker. This technology was once as rare in smartphones as a polar bear at the beach. Relegated to overclocked PCSAs, Apple themselves have hinted at future iPhones featuring integrated thermosiphon loops etched directly into the mid-chassis. But wait, you might be wondering, how does this magic trick stay sealed when the phone gets wet? The secret source powering these prototypes is Apple's own patents and tech. With Apple leading the charge, third parties quickly jump into action. Once liquid cooling takes off, the possibilities become endless. Quieter, denser, cooler chips enable entirely new. So despite the naysayers, the future is frosty. And I want to thank you all for joining me on this journey into the wild frontier of smartphone cooling.